I greet you good morning or good afternoon, depending on where you are. Maybe it's morning there, or it's afternoon, or it's night. Now, let's look at the Rankine cycle, which is, we are continuing with our thermodynamic lectures. Let's look at Rankine cycle. In the other lectures, we talked about Carnot cycle, where we had isothermal expansion followed by an adiabatic expansion, followed by an isothermal compression, and adiabatic compression. In the Rankine cycle, we are going to see later on how we can interface the Rankine cycle and the Carnot cycle. But Rankine cycle is typical of power plants, steam power plants. And unlike in the Carnot cycle, where we were talking of the fluid is basically the ideal gas, here the fluid or the fuel is water. So, the Rankine cycle, in the system we have a pump which pumps water from low pressure to high pressure into the boiler. The boiler is where we elevate the temperature of that fluid, that's water. It can be elevated to the point where we get a superheated steam, or we can get a wet vapor with a relatively high dryness fraction. And we also have a turbine where work will be done, and a condenser where the vapor will be cooled, so that again we recycle the process. So that basically in the Rankine cycle, the elements in the Rankine cycle, we can say are, we have the pump, we have the boiler, we have the turbine, and we have the condenser. So these are the key elements in the Rankine cycle. So let us represent the Rankine cycle in a schematic where we have temperature versus entropy. We have temperature versus entropy. S is entropy, and T is temperature. So we are going to look at it in the temperature entropy profile. Don't forget, when we dealt with the Carnot cycle, we were dealing with pressure volume profile. And when we interface the Rankine and Carnot cycles, you're going to see that they actually can be interfaced. But let me just talk first of all about some fundamental thermodynamic principles which are very important for you to understand before we deal with this system. One very important one is I want you to understand what Clausius inequality is, because this Clausius inequality relates the heat and entropy, and it's that ds, the change in entropy, is given by the change in the heat, or the heat supplied divided by temperature. So that when you are dealing with an isentropic process where the entropy does not change, no change in entropy, then 0 greater or equal to dq over t, which implies that dq is 0. Normally it's adiabatic. So if work is done under isentropic conditions, most likely it's also adiabatic. Very important for us to note that. And then the other one which I want you to note is the Clapeyron equation, which deals with phase equilibria. That is, the change in pressure with temperature is delta S, delta V. And so if you put in the expression for entropy there, if this is under constant pressure, remember then in that particular case, dq under constant pressure is the same as delta H. So we can have dq over T delta V, and that can be delta H over T if the pressure is constant, because we have used the fact that dq, the constant pressure, is delta H. These two fundamental thermodynamic principles are very, very important as we progressively move on with the Rankine system and keep on working with them back and forth. Now, in the Rankine system, like I've said, there is a pump. We have a pump. So let's do the schematic. We have a pump. And this pump pumps water from low pressure to high pressure. It's a pump to the boiler. Our boiler. So the boiler, heat is applied to the boiler. Then we have a turbine and a condenser. So we have a condenser. Heat is discarded from the condenser. And we have our turbine, where work is done. There's a work outputted from our turbine. It's work outputted from our turbine. So we have the pump. I repeat, pumps water from low pressure to high pressure to the boiler. In the boiler, the water is heated. It can be heated completely wholly into steam, or maybe into white vapor. In other words, it will be in the region where there's still some droplets of water in the continuous stream of the vapor moving. And then you have the turbine, where you feed that steam in the turbine, and of course it will do work, which could normally be shaft work. And then the condenser, where it is cooled down to liquid again, and then the cycle continues. Then the cycle continues. So if we represent this on the temperature entropy diagram, this temperature, repeat, entropy diagram, then we can think of a state point 1. Let's call that state point 1. So that the pressure is low there. Let's state point 1. So that's state point 1. And so in an isentropic process, we move to state point 2. And of course now, the pump pumps this water, which is at high pressure, pumps it, and we can form a superheated steam at state point 3. Or we can have this at state point 3 prime or 3 double prime. Now that corresponds to a wet vapor. So the wetness fraction normally is, mass of liquid, of water, mass of mixture. Wetness fraction. In terms of dryness fraction, which you call X, where that will be the mass of dry steam divided by mass of dry steam plus mass of liquid. And normally when you are dealing with dryness fraction, these systems, by the time it's going to the turbine, it's normally about 18%. And so you have pumped the water from low pressure to high pressure using your pump, which pumps it into the boiler. In the boiler, it is heated up. You could have a superheated steam, let's say superheated steam at state point 3. And then, of course, you will feed it into the turbine. Work will be done. The turbine work will be done. Then you'll be at state point 4. From state point 4, it probably doesn't have to stop at, it doesn't have to go to state point 4. It can go to state point 4 prime, or again, the wet vapor region, where we have vapor and liquid, that is state point 4 prime. And of course, the cycle continues. Now, I need to talk about the turbine. So that you understand what we are talking about. In the turbine, what are we talking about? Let us look at the Pelton turbine. Let's just draw a schematic of it. So let's just have our casing. Let's have our nozzle. casing. Let me put it a double casing. So that doesn't look so delicate. And we have the pipe which brings the steam. That's a pelton. That feeds in the steam into our system. So we have here is our nozzle. This is the spear. And of course we have a jet steam. So we have our runner here. Just a sketch. We have our runner. We have our vanes or blades. We have our runner here. And that is the casing. Now, nozzle, we are going to talk about the nozzle. Nozzle normally just enhances the velocity, the flow of the velocity of that particular steam, that particular system. Enhances velocity. That's basically what it does. So we have, in this particular case, notice that we have the steam jet or water jet. It's the blades. The process of generating work proceeds. So that's just the Pelton turbine. Now, when we are dealing with steady-state flow processes, the first law of thermodynamics changes significantly from steady-state flow processes. The first law becomes dH plus d of c squared over 2 plus g dz is equals to dq minus dw. And this second term, this first term deals with enthalpy. Take note. The second term deals with kinetic energy. And the third term deals with potential energy. And dq and dw are the usual meanings. You have talked of heat and work. So, we are assuming in the turbine that the kinetic energy does not change, is zero, and that the potential energy is also zero because there is no change in the elevation from the datum level, so we call that zero. And because the process is isentropic, if you remember the circle which we had from state point 3 to 4, state point 3 to 4 was an isentropic process. So if it's an isentropic, then dq is zero. dq is zero. We're dealing with isentropic process. Remember from the Rankine circle, from state point 3 to 4 is an isentropic process because there's no change in the entropy, because remember, our axis is temperature versus entropy. So dH is equals to minus dW. And so when we are talking of the steam being injected into the turbine, let us call that the entry, and then at the exit, so we similarly have 1, 2. It's work done as the steam enters the turbine, leaves the turbine. And of course, when it leaves the turbine, the pressure is significantly low. So, being a state function, this becomes H2 minus H1, and that will be equal to W. Remember, there's no W2 minus W1, I repeat, because work is a path function. So, what does it mean? It means that the work outputted from the turbine depends on the difference in the enthalpies at the exit at the exit and the entrance. The difference, the enthalpy at the exit and the entrance. Very important. And this will be determined significantly with the temperatures in the boiler. Because remember, H, all said and done, is heat transfer under constant pressure. So, and heat has to do with the boiler. So that's one way, that's a mnemonic of remembering what basically really affects this. And so here I've also drawn the nozzle. And it's important for us to also look at the nozzle, because these are important component which makes the turbine more efficient, So let's just look at the nozzle. Again, the nozzle can be diverging or converging. We have fluid 1, fluid 2, nozzle, nozzle. Nozzle can be diverging or converging. And like you have said, it enhances the flow velocity of the steam. Again, when you go to the first law, we say that dH plus dc squared over 2 plus gdz equals dq minus dw. Remember, in the nozzle, there's no work done. So, but the velocity is affected. The potential energy is 0. There's no change in the datum level. It's adiabatic, because you're dealing as entropic processes, and there's no work done. So that dH is equals to minus dc squared over 2. And so what does that mean? That means that H2 minus H1 is equals to minus C2 squared minus C1 squared over 2 when you solve that particular integral. And so if we assume that the velocity, the exit velocity is very high, if we assume that C2 squared much greater than C1 squared, because remember it has gone through the nozzle and it has been enhanced, the velocity has been enhanced, then you'll have H2 minus H1 is equals to minus C2 squared over 2. So if we remove the negative signs, you have H1 minus H2 is equals to C2 squared over 2. Cross multiplying, so we have 2 into H1 minus H2 is equals to C2 squared, or C2 is equals to square root of 2 H1 minus H2. So again, we are relating the final velocity is related again to the enthalpy differences, which you have said depends on the temperature of the boiler. So I repeat, the Rankine cycle has a pump which pumps in the fluid to the boiler where the heating takes place. You can form superheated steam or a wet vapor. So wet vapor means you're in the region where there's equilibrium between vapor and liquid. And of course, when you talk of those, there's also what's called the Lever's rule. It's able to tell you the moles of liquid and vapor when you look at temperature versus composition and so forth in phase equilibria. So all these things are married together. And we are also saying that you need, for example, for the turbine, you can add in a nozzle which makes it much more efficient. And we are seeing that work output from the turbine and also the behavior of the nozzle all are dependent on the temperatures in the boiler, because we are talking about the enthalpies in this particular system. So we'll stop at this particular point and we're going to look at other aspects of thermodynamics.